ELEC2 2019 question 7. Part A. Pulse code modulation, PCM, is used to convert a signal from analog to digital format, which can be transmitted over a digital communication system. The first part of the process is the sampled analog signal to produce pulse amplitude modulation, PAM. Complete the third graph to illustrate this process for a given analog signal and pulse train. So we've got our varying analog signal, we've got our sampling clock, and we've got 3 samples that need to be taken. Now for PAM, for each sample, the height of the signal is equal to the amplitude of the PAM output signal at that sampling clock instant. So as far as our output's concerned, so 2 boxes in when we've got our first sample, the height of the PAM is the height of the signal at that particular point in time. And what we can see is that it's about half a box high. So we've got to make it the same height as the sample clock. Okay, then the second signal, which is another 4 boxes on, we're at 2 boxes high. So what we need to do is draw our sampling clock here. So it's 2 boxes high. And then the third one is just over 3 boxes high, and that's over here. So as you can see, each of our PAM signals are in the exact time position that the sampling clock, sampling gate clock outputs are. Okay, part B. Complete the block diagram of a PCM receiver using the following subsystems. And we've got clock, DAC, low pass filter, Schmitt trigger, CPO shift register. Now these are basically block diagrams that you just need to know. They are in the ebooks. You can see I've already penciled in 4 boxes. We're then ascertaining exactly where the 5th box goes. But in terms of order, what we need to know is that the first thing that we get for one of these is a Schmitt trigger. This is then followed by the CPO shift register. Which in turn has the DAC after it, and then the low pass filter, which then goes to the analog output. We're missing the position of the clock. The clock would be here. And that links to the CPO. So the idea is we've got a serial PCM signal coming in on the input. Schmitt trigger gets rid of the noise. The CPO shifts that serial binary code into parallel binary code, and the clock does the synchronization in terms of how that works. This is then sent to the DAC, which turns that binary code into an analog signal. The low pass filter gets rid of any stray AC, which is unrequired, and then we've got our analog output. Okay, part C, part 1. Complete the circuit diagram for a 4-bit serial to parallel output shift register based on D-type flip-flops. Data is inputted started with the most significant bit MSB. Label the most significant MSB of the output D, the least significant LSB of the output A, and the serial input of the shift register. And we've got 4 D-types that we need to use in order to get this particular CPO. All right, so the first thing that you need to do with this type of configuration is label the clock. And for this particular configuration, all of the D types for a shift register are linked to the same clock. The next bit is the serial input. All right, so serial input is going to be from the left-hand side over here. And then we can label the outputs. Now, the outputs we're going to label A, B, C, and D, and they are all linked to the Q outputs. And for this particular CPO, A, which is the least significant bit, is on the left, followed by B, C, and D, which is our most significant bit. And because this is a shift register, the Q's are linked to the next D, so we're going to link these across. And there we've got our CPO. Okay, for part 2. Now this nationally wasn't answered particularly well, but the reality is if you know how a shift register works, then this is actually quite a straightforward question. We've got a serial input, we've got a trigger pulse, so our clock is going to clock 4 times in order for our serial input to start to shift. And what happens is for each clock pulse, you get a shifting of D to Q. And what this means is that the serial input on the first clock pulse will go into A and become A's output. And then on the next clock pulse, another 1 from the serial input will become A's output, and A's output will become B's output, and so on. So what we get is this type of situation where on this next clock pulse, all of these move in this direction. And what this means is that we're going to get a 1 here, a 0 here, a 0 here, and a 0 here. Now the same occurs on the next clock pulse. Which means that we've got a 1 for A, now a 1 for B, and a 0 for C, and a 0 for D. And then on the next clock pulse, we get exactly the same. And on the last clock pulse, all of A, B, C, and D are high. And this concludes question 7.